Welcome back everyone. In this lecture we will continue to prove more properties of irreducible root systems which will help us to understand more about irreducible root systems. So, as I said in the earlier lecture, we will try to understand the root lengths that occur for the various elements of this given irreducible root system. So, let us start with the irreducible root system phi irreducible root system. So, we claim that there exist at most two root lengths that occur in phi. Okay. So, this is the lemma. So, I guess this is the third lemma that proving about irreducible root system. So, there is at most two root lengths occur in phi, and in particularly if we take two roots alpha and beta. So, for alpha beta in phi and assume that the lengths of alpha and beta they are same. So, then there exists W in W such that this beta equal to W alpha. So, that means if two roots are conjugate, if and only if the length must be same. Okay, so let us see how to prove this. So, for this we need to understand the Cartan numbers or the ratio of this root lengths. So, recall that so this is something we already observed in the table that we have introduced in the very first root system. So, what we proved for any root system phi and then given any two vectors alpha beta is in phi. So, suppose alpha beta they are not orthogonal. Okay. If it is orthogonal, then we were not able to actually determine the ratio between the square of lengths. Okay. So, but whenever they are not orthogonal, so then what we proved that this norm beta square divided by norm alpha square that can be determined, and if you assume norm beta is greater than or equal to norm alpha, then exactly this is going to take value from 1 to 3. And in the other case, when norm alpha is greater than or equal to norm beta, then this will be exactly 1 by 2, 1 by 3. So, basically this ratio norm beta square divided by norm alpha square, this can take value 1, 2, 3 and often 1 by 3. So, now how one can use this in order to prove what we want. So, you start with arbitrary vectors alpha beta inside phi. So, this is something we fix. So, then what can happen, alpha beta could be actually orthogonal to each other. Okay. But then you can see that the span of W alpha, so that has to be exactly capital E. So, that is because this action of W on capital E is irreducible. Okay. E is irreducible representation, irreducible W representation, that is what we proved in the last class. So, that means if I take alpha, then if I look at the W orbit of this alpha, that must span this capital E, because this space is actually W invariant. So, then that forces that there exists W in W such that this W alpha comma beta, the inner product must be non-zero. If it is 0 for all W conjugate of alpha, then that would imply that beta will be inside perpendicular of E, but perpendicular of E is 0. Okay, that is a contradiction, because beta is non-zero to begin with, because it is a root. So, what we got some W conjugate of alpha such that this alpha and beta inner product W alpha comma beta is non-zero. Now, note that the length alpha alpha, so or the inner product alpha alpha is same as the inner product W alpha W alpha. Okay. Now, if you actually think about the ratio of this norm beta square divided by norm alpha square, then we already observed that this is same as norm beta square divided by norm w alpha square, because this is true. So, this ratio must be either 1 to 3 or of 1 by 3 whenever the inner product alpha beta is non-zero. So, that forces that this norm beta square divided by norm w alpha square, this has to be either 1, 2, 3 or 1 by 2, 1 by 3. So, basically even if alpha beta are orthogonal, we will be able to determine this ratio between norm beta square and norm alpha square whenever phi is irreducible. That is what we observe. Okay. So, this actually forces that we can't have 3 root lengths for elements of phi. So, because if you have 3 root lengths, that would definitely imply a ratio of the form 3 by 2. Okay. So, this is something I will leave it to you to check. You have to convince yourself that we will get 3 by 2. Okay. So, the 3 root lengths would imply the ratio that we are like norm beta square divided by norm alpha square will be of the form, okay. The ratio would imply that the ratio will take the form 3 by 2, which is absurd, because we already seen that these are all the only possibilities 1, 2, 3 of and 1 by 3. So, 3 by 2 cannot be possible. So, that leads us to contradiction. So, that means 3 root lengths cannot occur, only 2 root lengths can occur. So, that proves that at most 2 root lengths occur inside phi. So, now let alpha beta inside phi such that norm of alpha equal to norm beta. Now, as before, one can assume that alpha beta the inner product is non-zero, otherwise you replace alpha by the conjugate of alpha. Okay. So, now you can also assume that alpha not equal to beta, otherwise there is nothing to prove. Okay. So, in this case you can see that whenever the alpha beta is non-zero, so then this and the norm of alpha is same as norm of beta. This is the A2 type case. So, in this case the Cartan integers alpha beta and then beta alpha. So, this must be plus or minus 1. So, now if needed you replace beta by minus beta. So, then you can assume that this Cartan integer is always plus 1. So, if needed just replace beta by minus beta. So, then what it says, so this implies that the inner product beta alpha, so the Cartan integer associated with the beta alpha is also 1, because the inner product beta alpha must be positive. So, then you can see that S alpha of beta must be exactly beta minus alpha, and similarly S beta of alpha also must be alpha minus beta. So, now you can see that if you compute S alpha, S beta, S alpha on this beta, then you can see that this is going to be exactly equal to. So, S alpha beta will be beta minus alpha. So, this is S alpha S beta of beta minus alpha. So, then this is going to give us S alpha minus beta and then S beta of minus alpha, this is minus, this is plus minus. So, it is minus alpha plus beta. So, it is exactly plus alpha. So, that means alpha and beta are conjugate under this S alpha, S beta, S alpha. So, that means alpha beta are conjugate inside your W conjugate inside your Euclidean space. So, this is what we wanted to prove. So, we proved that. So, if given, so what is the summary? So, we did all this work to prove the following thing. So, we proved that if I start with irreducible root system, so then at most 2 root length can occur. In case if it has 2 root lengths, let us say this phi has 2 root lengths. So, then what we can do, we can talk about short roots and long roots. So, in this case we can talk about short roots and long roots, and naturally they are defined. And if we actually has only one root length, so in that case by convention we just assume all roots are long roots. Okay. If we has only one root length, so then by convention we assume that, or we just say all the elements of phi are long roots, all elements of phi are long. Okay. So, this is the convention that we always use. So, now in case phi has actually 2 distinct root lengths, so then we can say something about the maximal root that we actually defined in the earlier class. Okay. So, let us say what it is. So, as expected it will be always a long root. Okay. So, let phi be irreducible with distinct root lengths, with 2 distinct root lengths. For example, B2 and G2 they have 2 distinct root lengths, both are irreducible, that is also easy to verify, and they have 2 distinct root lengths. So, then the maximal element with respect to the partial order that we define. So, then the maximal element that is unique or root beta. So, this is with respect to the partial order. So, this is always, you can prove that it is always long root. Okay. So, this is something very important. So, how one actually proves this? So, again like we have to use the W conjugate action. So, what we can do, you start with alpha. So, then there exists W in W such that W alpha is inside the fundamental chamber. So, you can replace alpha by W alpha. So, you can assume that this alpha is actually coming from phi intersection this closure of the fundamental chamber. So, take alpha which is in the inside this pi intersection the closure of the fundamental chamber. Okay. So, this can be obtained by replacing alpha by some conjugate of alpha. Okay. So, now since beta minus alpha is always positive. So, beta minus alpha is positive, that is we have already observed. So, then we have immediately for this alpha. Okay. So, for any gamma inside this closure of the fundamental chamber, we have that gamma times this beta minus alpha, this inner product is always greater than or equal to 0, because beta minus alpha is positive, and this is true for all gamma inside the closure of the fundamental chamber. So, now what we can do, we can apply for gamma equal to beta, because all the positive roots are inside your closure of the fundamental chamber. So, if we take gamma to be beta, so then you can see that that will give you beta comma beta minus alpha is also already non-negative. So, that implies that beta beta must be greater than or equal to the inner product beta alpha. So, now you apply gamma equal to alpha. So, then that would imply that alpha comma beta minus alpha is greater than or equal to 0. So, that forces that the inner product beta alpha is greater than or equal to alpha alpha. So, that means if we put them together, then the beta beta is greater than or equal to beta alpha, which is greater than or equal to alpha alpha. So, in particularly for any alpha, what we proved that the inner product beta beta must be greater than or equal to alpha alpha. So, that implies that beta must be long root. So, that is always the case. Okay. So, this is actually kind of ends all the important properties of the irreducible root systems. So, now let us see how one can associate this Cartan matrix for any root system, and then how one actually uses the Cartan matrices in order to classify the root systems. So, here is this new idea, what is called Cartan matrix of any root system phi. So, this is something naturally motivated. Okay. So, why it is naturally motivated? So, we already seen that if we fix the base pi base capital pi inside phi. So, then somewhat the elements of phi, they are controlled by pi. So, we indeed proved a result, any positive root can be written as sum of simple roots, let us say beta 1 plus etcetera beta k, such a way that whenever you just break at some point like beta I plus etcetera beta k, that must be again a root. So, that tells us that any root can be obtained from like combination of this simple roots of pi, and every successive like that combination is again a root. Okay. So, that in some sense motivates at that pi is indeed kind of generates phi. So, more or less pi possesses all the information about phi. So, let us make that more precise. Okay. Let us say E is the Euclidean space that contains phi, and then dimension of this E is L. So, in particularly I can label the elements of pi or the order elements of pi to be alpha 1 etcetera alpha L. So, now given this alpha i's, we have this natural matrix. So, this matrix we call it Cartan matrix. So, this is the Cartan matrix. What it is? It is given by the ijth entry is the Cartan integer alpha I alpha j, where I j varies over from 1 to L. So, this L by L matrix clearly is actually invertible matrix, because this alpha I is the form of basis of capital E. So, this matrix must be invertible. So, if you think about it, we already seen that this matrix is actually related, closely related to the inner product, since capital pi is actually basis and the inner product is positive definite, and this is all like you take this alpha I, the inner product alpha I alpha j, this matrix. So, this is going to be positive definite matrix, and this matrix obtained from this matrix by scaling each row by this 2 divided by alpha I. So, that means this Cartan matrix is also positive definite matrix. So, it is not just invertible matrix. So, this is actually indeed positive definite matrix. So, this is something I will leave it to you to check. There is nothing to check, you have to verify that is the case for this matrix. So, now we will show that this Cartan matrix more or less possesses all the information about the root system. So, what is the meaning of that? So, if you know the Cartan matrix, then we can recover the root system entirely. Okay. So, before that, let me leave one exercise for you. So, you can just directly compute the Cartan matrices for the 2-dimensional root system, and it is not hard to see. If you take A1 cross A1, then this is the Cartan matrix 2 0 0 2, and then for A2 the Cartan matrix is 2 minus 1 minus 1 2, and of course, alpha beta the base chosen to be the natural vectors alpha beta. Okay. So, the B2 will be exactly given by 2 minus 2 minus 1 2, and then G2 is exactly given by 2 minus 1 minus 3 2. Of course, there is some order that we are fixing. It is not that hard to figure out what is the order that we are fixing. Okay. So, let us understand this association. We started with phi and then we associated what is called this positive definite matrix, Cartan matrix, which we call it C of pi. So, C of pi, it is an L by N, it is a L by L matrix given by the entries or just the Cartan integers associated with this roots alpha and alpha j. So, this is the matrix 1 less than or equal to I j less than or equal to L. And what we want to prove? We want to prove that this Cartan matrix entirely actually determines the root system. But before that, let us see why this Cartan matrix is actually somewhat unique up to order with respect to the root system, because there is a choice involved already. To define the Cartan matrix, we have made a choice. What is the choice? The choice was the base. We have fixed the base to define the Cartan matrix. So, now why the base, the choice of the base does not affect the Cartan matrix? Of course, it will affect up to the order, but up to the order why it will not affect? That is because any two given bases are conjugate. So, again I will leave it to you to check. So, this is not very hard. If you start with pi dash and pi, both are, let us say, bases. So, then what one can prove? One can prove that there exists of course W in W such that W pi dash is equal to pi. So, now what one can prove, if you take this Cartan matrix associated with pi dash, so then that is going to be exactly equal to the Cartan matrix associated with pi. So, since this W is isometry and in particular it preserves the inner product. So, it preserves actually the Cartan integers. So, it is immediate that the corresponding Cartan matrices must be same. Of course, up to the order there is no issue. So, now what we have done, so we have taken this set of all isomorphism classes of root system and then defined a map from that set to the set of all this Cartan matrices, or this is sitting inside the set of all positive definite L by L matrices. So, now what we are going to show? We are going to show this map is actually gives one to one correspondence onto that image. Okay. In particularly, we want to prove that the Cartan matrices are uniquely determining the root system. So, that is the theorem. So, what is the theorem? Okay, let me state it very explicitly. So, you take phi dash to be another root system sitting inside E dash, and then let us say phi dash and phi both have same Cartan matrices. Okay, let us fix these notations. Let us say phi dash sitting inside is E dash, this is another root system, and with this base pi dash. Okay, we already have this phi sitting inside E with the base pi. Okay, this is already there, and you also have this Cartan matrix which is given by alpha alpha j and 1 less than or equal to I j less than or equal to 10. So, all these data are already given, and we let us say we have another phi dash pi dash, and for some reason if we know that these two Cartan matrices are same, that means all the ijth entries must be same. So, the Cartan integers associated with alpha and alpha j is same as alpha I dash alpha j dash, where alpha I dash we just call the elements of pi dash. So, this is alpha 1 dash etcetera alpha L dash. Okay. So, note that the dimension of the root system or the rank of the root system must be same to begin with, or otherwise you can also recover that from knowing the dimension of the Cartan matrix, because Cartan matrix is L by L matrix. So, both the dimension of E and E dash must be same, because that is you can get it from the dimension of this Cartan matrix. So, now if this is true, the Cartan integers are same for all 1 less than or equal to I j less than or equal to L. So, then what one can prove? The bijection that we have from pi to pi dash, which sends alpha I to alpha I dash. So, that can be extended uniquely to an isomorphism. So, this bijection extends uniquely to an isomorphism say that isomorphism is pi from E to E dash, and again such a way that this also maps phi in onto phi dash. So, this mapping phi onto phi dash and satisfies the following property, satisfying the Cartan integer associated with phi alpha phi beta must be same as the Cartan integer associated with alpha beta for all alpha beta is in phi. That means, this pi that we have extended defines isomorphism between this root system phi and phi dash. So, that means, if C of pi is same as C of pi dash, the Cartan matrices of pi and pi dash are same, that immediately implies the corresponding root systems are isomorphic. And it is not hard to see, if you start with isomorphic root system, then the Cartan matrices must be same up to an order. Okay. So, let us prove this. So, this is again not very hard to prove, we have developed enough language to prove this. So, note that pi and pi dash both are basis of E and E dash respectively. So, in particularly the bijective map that we have from pi to pi dash. So, which is given by alpha I goes to alpha I dash. So, this can be uniquely extended as a linear isomorphism from E to E dash, because both pi and pi dash they are basis for E and E dash respectively. So, this isomorphism that it is there already. So, we fix that. So, if alpha beta both are elements of pi, so then we get the following. So, because the Cartan integers are same. So, in particularly if we apply S of pi alpha on pi beta, so then it is immediate that, so you can do the calculation and then see this is exactly pi of S alpha of beta. So, that means, if you look at this commutative diagram, E to E dash you have pi, and then E to E you have S alpha, and then E to E dash you have again pi, and then E dash to E dash you have S of alpha dash which is pi of alpha. So, then this diagram actually commutes, that is what this equation tells us. So, that means, if you take pi S alpha pi dash, that is going to be exactly S pi of alpha. So, that is what we are getting for alpha in capital pi. But note that your while group is actually generated by simple reflections. So, since it is generated by simple reflections, this map that we have from E to E dash, that naturally actually gives us map from the while group W to double dash. So, what is the map? On the generator we already have this map pi S alpha pi S alpha pi inverse is S pi of alpha. So, that means, from W to W dash we can define W goes to pi W pi inverse. So, that is going to be easily you can verify, because this is a conjugation where conjugation is coming from where the pi is actually element of your GL of E comma E dash. So, that means, so this is isomorphism from E comma E dash, and since pi W pi inverse lies inside W dash for all W, because it is the case for simple reflection S alpha, and capital W is generated by all the simple reflection S alpha coming from pi. So, that proves that pi W pi inverse must be element of W dash. So, since this is just a natural map, well defined map, so this is definitely an isomorphism between the groups, that is easy to check. So, now since W and W dash are generated by simple reflections, you can see that this is a group isomorphism, and S alpha is actually mapped to S alpha dash under this map for alpha in pi. So, now for any beta that is coming from pi, you can see that there exists W in W such that W inverse beta, which we call it alpha. So, that is in pi. So, then this means W of alpha is equal to beta. Okay. Now, go back to pi of beta and then see what happens. So, pi of beta is going to be exactly equal to pi of pi W pi inverse of alpha, pi inverse of pi of alpha. Why? Because pi inverse pi will get cancelled and W of alpha is beta. So, that is going to give you exactly pi of beta. So, now that means, so these things can be combined as W dash, which is an element of capital W dash, and pi of alpha is an element inside your pi dash. So, that means, so this is going to be W dash alpha dash. So, which is an element inside W dash pi dash, which is exactly pi dash phi dash. So, that means pi of beta is inside phi dash for all beta inside phi. Okay. And again you can see that W pi is equal to phi. So, and W dash pi dash is exactly phi dash, and since pi W pi inverse is exactly equal to W dash and pi of capital pi is pi dash. So, this information immediately implies if you apply pi on phi, so then we get exactly pi of W pi. So, then you can see that this is W pi inverse pi of pi dash. So, then this is exactly W dash pi inverse, sorry. So, we can just take it to be, this is just pi. So, then this is just W dash pi dash, which is phi dash. So, this proves that pi maps phi onto phi dash. So, since pi is an isomorphism, pi restricted to phi must be injective. So, this is gives you bijective correspondence between phi and phi dash. So, now it is not hard to see if you take alpha beta in phi. So, then using the formulas, so for alpha beta is in phi, we can see that S alpha beta must be exactly beta minus the Cartan integer beta alpha alpha, and since pi S alpha pi inverse is exactly S pi alpha alpha. So, you can see that S pi of alpha applied on pi of beta must be exactly pi S alpha pi inverse applied on pi of beta. So, this is going to be pi S alpha of beta. So, which is exactly pi of beta minus, again this Cartan number will stay as it is, and then pi of alpha. So, this is what we get one hand, but on the other hand S pi of alpha pi of beta, by definition it is going to be pi of beta minus the Cartan integers pi of beta pi of alpha pi of alpha, and since these two are equal. So, that forces that the Cartan number beta alpha must be same as the Cartan number pi of beta pi of alpha, and since this is true for all alpha beta inside phi. So, we get this map pi that we define is an actually isomorphism between the root systems. Okay. So, this means if C of pi is same as C of pi dash up to an order, so then up to an reorder, then this says that the corresponding root system must be isomorphic to each other. So, in some sense up to a reorder, the Cartan matrix uniquely determines the root system. So, in the next class maybe I will tell you like how one can practically recover the root system by knowing all these Cartan integers. Okay. So, maybe I will do it in the next class. I will stop here because we are running out of time. Thanks.